Hello everyone, my name is Carl. Welcome to my workshop and welcome to my YouTube channel. This is going to be the preamble to what will become part 9 of the Harrison Mill Resto, where we'll be making the cast iron housing for the bronze lead nut that we made in episode 8. So in this episode we're going to be looking at the design of the housing, and we're going to be machining a register on the cast iron piece itself so that we can get it into the chuck. So without further ado, let's get on with it. Okay, so this is the item that we're going to be manufacturing in the lathe. This is the nut housing for the nut that we made earlier, the bronze 5 Acme nut. And as you can see, you'll remember from when we looked at this previously, it's got this huge chunk of damage on it, and this crack down here. Here comes the first best scriber, second best pointer. So this is what we're going to be making, and so we've got this taper here that we've got to produce. This is 2.75 inches, this base diameter, and 2.5 inches at the top. Then we've got this 1.75 inch bore, which is a locating feature for the nut. Now, because of this crack, the top of this is about 1/4 thou bigger than the bottom. So when I measured this, I measured down here where the diameter is more likely to be as it was when it was first manufactured. And this came in at exactly 1.75 inches. So basically that makes, if the nut is 1.75 inches, which it is, then that's basically a transition fit essentially. So we've also got this recess here to allow this to seat correctly, and we've got a PCD, if I can get that into camera, on camera rather. We've got these 3 holes which are for the 1/4 UNC mounting bolts. Now you'll notice that they're actually 120 degrees apart, which is really good for us to work out this PCD, because that makes that basically an equilateral triangle circumscribed by a circle, which is the PCD. So I'll be showing you how I'm going to calculate that PCD in a little while. We'll go through the drawing on the whiteboard first. So functional dimensions on this component are going to be this face here and this bore here. They're required to be orthogonal in order to basically put the nut in the correct geometric relationship to the rest of the parts of the milling machine to make everything run correctly as it should. So we'll be forming these dimensions in one setting, and that will also mean that this this face here will end up being orthogonal to this face. It doesn't actually have to be, but it will be, because we'll be forming this in one setting as well, in the same setting as we do this face and this bore. So we'll do this face and the bore at the same time. So we'll take you over to the whiteboard now, and we'll have a look at the drawing for this that I've made, and we'll talk about a few more points. Okay, so let's take a look at the sketch of the part that we're going to make for this the nut housing. So the material we're going to be using is grey cast iron. It's continuously cast, and that gives us a number of benefits over traditional grey cast iron. We'll talk about those a little bit more once we get the piece into the lathe. Now you can see again on this, I'm using the first best pointer this time. On the drawing, or the sketch rather, I've used colour again to indicate functional dimensions, which are going to act as locating features. So we have in red here, we have the base of the component, then we have the bore, and also the recess, which isn't a locating feature but will end up being coplanar to the base, because by very nature of being machined in one piece, and this this side here as well, this side face, which will also end up being orthogonal and coplanar, orthogonal to the base and coplanar to the bore. Just by virtue of being machined in one sitting, or in one setting rather even. So we have the bore here, which is 1.75 inches plus 5/10 minus 1/10. I'd rather go under than go over on this, because I want it to be a transition to a light interference fit, basically, when it's in there. And then obviously the base is going to be sitting on the bed of the machine, or rather the base of the machine, and that needs to be orthogonal to the bore in order to give so that the bore ends up being basically on the axis of the machine of the knee itself, so that once the screws in here, it can thread up and down, and it'll be correctly orthogonal to the table of the machine and the knee of the machine. The taper here and this face, they basically are not functional dimensions, they're aesthetic dimensions. So we'll actually have this piece turned around in the chuck to do that, so they don't really matter. However, what I'm going to do is use the 4-jaw. When I rotate this, I'll put this in the piece in the 3-jaw, and I'll machine these features in the 3-jaw and the bore so that they're all in the correct relationship to one another. And then I'm going to set this back up in the 4-jaw, although that's not strictly necessary, because I want this top face here to be square, or to be orthogonal rather to the bore as well, so that when the nut sits in, it's not just locating on the primary locating feature, which is this, obviously this cylindrical face, but I want this shoulder here on the nut to sit flat against this top here. So we'll do that in the 4-jaw, and we'll produce these in the 4-jaw. So they will end up being in an orthogonal and coplanar relationship to these other pieces, or these other features rather, but they don't need to be. That's you know, it's just going to be a byproduct of being in the 4-jaw to do this face. Now the taper that we've got here, the top is 2.5 inches and the bottom is 2.75 inches, the same as the recess, and the length of the taper is 1.5 inches. So if we look down here, you can see I've written the equation for working out a taper angle. So the tan of the angle is the large diameter minus the small diameter divided by the length. So that's 2.75 minus 2.5 divided by 1.5. That gives the tangent of the angle of the taper as 0.16, and that puts the angle at approximately 9 degrees. So we'll set that up. That's how we'll produce this taper using the compound slide. We'll set it to 9 degrees and we'll produce that taper. We've also got here, I've just drawn in the bore for the mounting bolts. We'll talk about them more when we've got the part machined and we've got this set up on the mill. But you can see there it's to suit a 1/4 UNC bolt, and it's counterbored because they're socket-headed cap screws that we're going to be using to mount this. The ubiquitous 1/4 UNC on this machine. So speaking of that, we've also got a PCD to put in there as well, which we'll do once we've got this machined. The PCD, as I mentioned when I showed you the actual component, or the old component, is 3 holes, and they're basically 120 degrees spaced around this PCD. So we need to calculate what this PCD is, and the beauty of this is that because we've got these 3 holes and they're 120 degrees apart, we have an equilateral triangle circumscribed by a circle, the diameter of which is our PCD. So I'm now going to take you over to the machine, or the mill itself, and we're going to do some measurements to work out what this dimension is here from point to point on these holes, and then I'm going to show you how from that we can calculate what this PCD is. So we're down and dirty on the base of the machine. This is where the nut housing fits on. I've got 2/4 UNC bolts screwed in with a couple of washers on each one, just to lift them off the mounting face slightly. And I've measured the width of the heads and recorded that. So in order to use this this circumscribed circle method, I need to know the distance across here between these 2 points. So we'll measure that now. We'll get in with the mic and take a measurement across there. So a straight line measurement basically between these 2 points. Let's get that on. Okay, so what we've got there is 3.513. So we'll take this over now to the whiteboard and we'll do some calculations, and I'll show you how we're going to work out this PCD. Okay, so it's time for some more whiteboard action. We're going to look at how we're going to calculate this PCD. And you remember I said that we were fortunate that we had these 3 holes for our quarter UNC mounting bolts on the housing at 120-degree spacing, because we have this equilateral triangle, which I've tried to draw as best I can freehand here, which is circumscribed by a circle, and the circle is the PCD, or the diameter of that circle is the PCD, I should say. So why were we so interested in measuring the distance from these 2 points, from 2 of the holes? We can call this distance A, and I'll show you why we were so interested in doing that now. And that's because there is a geometric and trigonometric identity for the radius of a circumscribed circle around an equilateral triangle, and that is this distance here, A. If we put that over √3, that gives us the radius of the circle. So the radius of the circumscribed circle about this triangle is A over √3. And I can show you why that is in another video if you want. I'll give you the proof of that. If you want me to do that, then please tell me so in the comments. Otherwise, I would advise you to, or I'd certainly strongly suggest that you have a look at this and read about it elsewhere. But I can walk through it if you want me to, and I'll do that in a separate video. Now, I measured the width of the head of the bolts before I started, and it came out as 0.369 inches. And you remember I said just now that this distance here, A, that I measured, or rather the distance I measured across the head of the bolts was 3.513 inches, which means that the distance point to point here for A between the centres of these holes is 3.513 inches minus this 0.369, which gives us 3.144 inches. So now if we put these numbers, if we plug them into this equation, we can see that our PCD is 2 times 3.144 divided by 1.732. Now the 1.732 is √3. So it's 2 times that, because this gives us the radius and we want the diameter. So 3.144 over 1.732 multiplied by 2 gives us a PCD of 3.63 inches. So the diameter of the circle, our PCD, is 3.63 inches. So here you would have a nice piece of continuously cast grey iron. And the benefits of this for us are legion. Because it's continuously cast, it doesn't have any built-in stresses as a sand casting would do, and this was almost certainly a sand casting when it was made. Harrison used a couple of foundries. They used one called Hunprenco, and I think they used Qualcast quite a lot as well, according to the research I've done so far anyway. But this stuff is produced in continuous sections, so it doesn't have, as I say, it doesn't have any inbuilt stresses because it cools much more uniformly than would a sand casting. It has a much finer and more uniform grain structure. It's got much more homogenized properties, and when we machine it, it machines very well anyway because it's full of graphite, being grey cast iron. The graphite is much more widely and more freely dispersed in the microstructure than it would be if it was a sand casting. And also, when it chips, it produces nice curly chips. It's still quite mucky because of the graphite, but it does chip quite well. So we're going to do a bit of machining on this now. You can't see very well the way this is held in the chuck. There is a bit of an air gap between the back of the jaws and the back of the piece. It's not very square where it's been cut. So what I want to do, we're going to have to do some fairly heavy turning on this to get it down to the dimensions that we require. So what I'm going to do initially is just take a skim off this outside edge. And another thing about being continuously cast actually is that it doesn't really have, apart from a bit of mill scale, any kind of hard skin on the exterior, because it cools much more uniformly than does a sand casting. So we'll take a skim off this outer edge, and then we'll face this surface here, so that we get a nice square and orthogonal piece that we can then put in the chuck, and it'll sit flat against the back of the jaws and also be held square to the jaws. So then we've got a really good hold of it, and we can do the heavy machining that we need to do without any fear of it moving in the chuck or giving us any other kind of orientation problems. So we'll do that now. So as much as I was waxing lyrical about the virtues of grey continuous cast iron and how nice it is to machine and all the rest of it, one of the things that you have to bear in mind about it, of course, is it is a cast product, so it's very rarely round, not even nearly so in this case. So I gripped it in the 3-jaw. It's just held here just by the cylindrical surface. It's not hard up against the back of the chuck jaws as I would like it to be. So what we've done is we've gone and basically machined the cylindrical face until it's round, and we've faced here. So we now have this true and square 2 faces that we can put up against the chuck, and we can get it gripped properly, and we can continue with the heavier machining that we have to do to get this down to the dimensions that we want. So that's your lot for this one, folks. Hopefully there is something of interest in this for you. We've got the chucking register machined now, and we've got the piece in. Unfortunately, I'm not going to be able to have enough time to do any more work on the piece, because I've got some work commitments coming up for the next couple of days. So I'll be away from home for a few days, just to do some bits and pieces for work, and then when I come back I can carry on with making the housing. So part 9 of the Harrison Mill Resto, or part 9B I should say, it probably will be titled by that point, will be coming up in the next couple of weeks. So I hope this tides you over until then, and gives you something to think about, and hopefully you get something out of it as well. Thanks very much for everyone who's come along and subscribed. We've had a couple of new subscribers since the last video, so thank you very much to that. Basically, you're making my dreams come true by allowing me to have my own YouTube machining channel, which is something that I've wanted to do for a long time. So thank you all very much for that. So we'll see you on the next one. Take care of yourselves, and see you soon.